Hello, welcome to the lecture series on control systems engineering. So far we have discussed about time response analysis. How exactly a system responds to step, ramp, parabolic, impulse input, then time response specifications like rise time, peak time, overshoot, time constant, settling time, steady state error, all these things we have studied. And finally, how exactly a controller can be used to fix the time response specifications. Also, we studied about root locus plot, how parameter k of the system can be chosen to achieve the required time response specifications. Now we'll start with frequency response analysis. Okay. Suppose I have a system. To this system, let us say I'll give a sinusoidal input. Let us say A sin omega t. A is the amplitude, omega is the frequency. This is the system. And I'll get the output. Let us say B sin omega t plus 5. So output amplitude may change, but input frequency, output frequency, they remain the same. But in the output there will be a phase shift, a delay. So as I vary this frequency, now there are two factors here, output amplitude by input amplitude. Okay, let us say magnitude ratio. And another one is the phase shift. If I go on varying the frequency, what happens to this? And what will be the phase shift? That we can study under frequency response. So the frequency response is defined as the magnitude and phase differences between the input and the output sinusoids. So you may use an amplifier for which you may give a sinusoidal input. Correct? There are many devices where you will be giving sinusoidal input and looking at the output. So now, what are the various ways we can understand how exactly frequency response of a system will be? So one way is we draw polar plot. Another way is we draw Nyquist plot. Bode plot. Like this. These plots we plot, basically we'll be plotting magnitude versus phase angle, magnitude versus frequency, correct? Phase angle versus frequency. These plots we draw. From this plot, we can analyze the system stability, system's relative stability, for sinusoidal inputs. Okay, right. So that is the idea. First, let us start with polar plot. It is the plot of magnitude ratio versus phase angle for different values of frequencies on polar coordinates. So G of S, H of S, open loop transfer function will be given to you. You have to find the magnitude and also have to find the phase angle. Then I create a coordinate system. This I call it as a real part of G of S, H of S. And this is imaginary part of G of S, H of S. I call it. And I call it as G of S, H of S plane. Okay. This I'll consider it as 0 degree plus 90 degree plus 180 degree plus 270, 360, so on. If I go in the counterclockwise, positive, clockwise is negative, minus 90, minus 180, minus 270, and so on. Okay, on this plane we will draw the polar plot. What is the procedure? Let us, as I mentioned earlier, open loop transfer function to system will be given, this one. Substitute S equal to j omega to convert into frequency domain. Also we are interested only steady state part of the response. Then we'll write magnitude and phase angle equations. Then we'll calculate magnitude ratio and phase angle for different values of frequencies. Then we'll draw the plot. First, let us learn how to draw the plot. Subsequently, we will establish the stability criterion. Then, whether such a system is stable, correct, how to make it stable, all such issues we will discuss. Now let us learn how to draw magnitude and phase angle equations for the poles and zeros. Suppose simply G of S is equal to S plus A. It's a 0. I'll substitute S equal to j omega plus A. Magnitude is modulus of G of j omega. So modulus of j omega plus A is the real part, imaginary part. So it will become under root omega square A square. You get it. And phase angle will be tan inverse of omega by A. You will get. Next is G of S equal to 1 by S plus A. So substitute S equal to j omega, again j omega plus A. Magnitude is modulus of G of j omega. So this is what you get. This will become under root omega square plus A square. Phase angle B, this is a pole, that's why minus, it's in the denominator, tan inverse of omega by A. Because you know you have studied in complex numbers, x plus j y or iy is there. What is a complex number? Magnitude of a complex number is modulus of x plus jy, and then modulus of that will become x square plus y square. And phi is equal to, the angle will be tan inverse of y by x. So if you represent, this is real part, this imaginary part. So real part is say x, imaginary part is say y. So this is the point we are talking about. X plus jy means distance of that from the origin. Suppose this is x, this is y. This will become root of x square plus y square. And this is angle phi. Tan phi is y by x. So y tan phi is tan inverse y by x. That's how we can convert these numbers as per this. Okay. It is s minus a. In this case, pole is on the left hand side. S equal to j omega. Magnitude is modulus of this means 1 by under root omega squared plus a squared only you get. Angle, if I calculate minus tan inverse omega by a means I'll get this angle. But what you need is this angle. That's why 180 minus of this you make it. Okay, this is this part. This minus because it is a pole. Same way, g of s is equal to a minus s. Okay. Now instead of it is s minus a, it is a minus s. So the point will be now, what is it? A is real, omega is imaginary. The point is here. Okay. So we can measure the angle straight away from here. So minus, because it is a pole, tan inverse minus omega by a. So minus of minus it will become plus tan inverse omega by a. In this case, you see here, it is minus a plus omega. It was here. We have to measure this angle. In this case, if it is here, can measure this angle. Right. G of s is equal to 1 by s. Means here we say there is a pole at origin. G of j omega is 1 by j omega. It is minus, magnitude is under root 0 square omega square, you will get omega. Now minus tan inverse, you can say 0 plus j omega. Omega by 0 is infinity. Tan inverse infinity is minus 90 degree. Every pole at origin, correct, will give, contribute minus 90 degree. Instead of pole at origin, suppose if you have a 0 at origin, then it is, again you can write 0 plus j omega. It is magnitude will be omega. Phase angle will be plus 90 degree. Okay, right. If there are n poles at the origin, then you write minus 90 into n, where n is the number of poles. If there are m zeros, then 90 into m. Right. Simply, there is a constant gain factor k, magnitude is k. Phase angle should be taken as 0 degree if k is positive, because it lies here. K should be phi should be taken as minus 180 degree if k is a negative value. Suppose you come across a factor, let us say e to the power of minus s, so j omega. e to the power of minus jy. So it is cos omega minus j sin omega. Magnitude will be 1. Angle will be minus omega. To convert into degrees, pi radians is 180 degree, omega radians is equal to how many degrees. So this way we can find out its magnitude and phase angle. I've just taken the kind of terms that we come across in open loop transfer function, and I have listed all this magnitude and phase angle equation so that you should not face any difficulty while writing magnitude and phase angle equations. So after calculating, as I mentioned, you consider the coordinate system. As I mentioned, this is the real axis. We call it as RE G of S H of S. This imaginary axis, we call it as IM G of S H of S. 0 degree plus 90 plus 180 plus 270 and so on. Then 0 minus 90 minus 180 minus 270. So this is the GH plane. On this plane, you have to draw the polar plot. Let me start with a simple example. Suppose G of S is equal to 10 divided by S plus 1 is your open loop transfer function. I have to draw the polar plot for that. So substitute S equal to j omega plus 1. Magnitude is modulus of G of j omega. Modulus of 10 is 10. And modulus of j omega is under root omega square plus 1. Phase angle is tan inverse of this. This is a constant 0. This is a pole, so minus tan inverse omega by 1. You'll get minus tan inverse omega. So omega, this is the magnitude equation. This is the phase angle equation. So for calculation purpose, I have simply given some arbitrary values 0, 0.2, 0.4, 0.6, 0.8, 1, 2, 3, 4, 5 and all that. If magnitude omega is 0, this is 0, 10 you will get. Tan inverse 0, 0 you get. Similarly, omega is 0.2, you substitute, you get the magnitude. Then you will get the phase angle. For 0.4, you will get the magnitude, you will get the phase angle. Like that, you calculate all these things. Okay, probably you can write a simple program or do it. Later, anyway, we have MATLAB, we can do this one. After that, now draw the coordinate system. Call it as REGH. Then you call this as IMGH. Then we call this as GH plane. This is 0 degree line. Then after that, minus 11 degree line you draw. Then minus 21 degree line you draw. Minus 30 degree line you draw. Say 38 degree. 45 degree. 63 degree. 71 degree. 78 degree. 84. Then minus 90. Okay. Now on 0 degree line, mark a magnitude of 10. This length is 10. 11 degree, 9.8 along this line. 9.28 along this line. Choose a proper scale and do it. 8.56. 7.80 like this. And mark here 0. Then you join all these points. Here you can write omega is equal to 0, magnitude is equal to 0. Magnitude is 10. Here you can write omega is equal to infinity, magnitude is equal to 0. And you can put an arrow like this varying like this as omega increases. Okay, so output by input amplitude ratio will be 10 times. But as you go on varying the frequency, the magnitude ratio keeps decreasing and finally it will become 0. That's the meaning of that. You know it's a type 0 problem. This is the polar plot. For type 0 problem, starting point will be a finite value and magnitude will be normally 0. Right. So it is 6 s plus 1 s plus 2, 6, then j omega plus 1 j omega 2. Modulus of 6 is 6. Modulus of j omega 1 is under root omega square plus 1. This is under root omega square plus 4. Phase angle of this will become 0. Phase angle of this will be minus tan inverse omega by 1 and minus tan inverse omega by 2. So this becomes phase angle equation. So there are two poles. You have to add the angles. Okay. So again omega magnitude equation 6 divided by under root omega square plus 1 omega square plus 4 and phase angle. Again I have chosen the same set of values of omega and I have calculated the magnitude by substituting in this. Also I have calculated the phase angles. As I mentioned earlier, again draw the coordinate system. Draw this line. And here omega equal to 0, magnitude is equal to 3. Okay. Here omega equal to infinity, magnitude is equal to 0. So then mark the values, join them. So one observation you make, in the previous problem there was only one pole. Because angle was 0 to 90 degree. Now addition of pole will contribute another 90 degree. Okay, it will be like this. Suppose there are 3 poles, the plot will be like this, 270. There will be, if I add one more pole, it will be like this. There is one pole. There are 2 poles here. There are 3 poles here. There are 4 poles here. Correct? Right. So in this case there are 3 poles. You know how the plot should be now. Okay. We'll continue in the next session working out some more examples. Okay. Practice this please.